Okay, so welcome back to section 2.3. We were right in the middle of finding alpha, beta, and gamma for the vector 2, 3, 5, right? So we figured out that the norm of the vector is the square root of 2 square plus 3 square plus 5 square, and that turns out to be the square root of 38. I hope you got that right. The cosine of alpha then is the first coordinate 2 divided by the square root of 38. If you take the inverse cosine, and by the way, the inverse cosine is nice because it's always between 0 and 180 degrees. And so you will never get negative numbers. And that's exactly how we measure the angle between two vectors, between 0 and 180 degrees. So you can always take the inverse cosine of these values, the directional cosines. So alpha, oh, by the way, this is a picture of the vector 2, 3, 5. And alpha turns out to be this angle here. And it's hard to see from this picture, but that angle is 71.1 degrees, or the inverse cosine of 2 divided by the square root of 38. The cosine of beta, which is this angle here, turns out to be 3 over the square root of 38. And therefore, the angle happens to be about 60.9 degrees. When you use your calculator, make sure this is set in the degree mode. On your homework, you may have to switch between the degree mode and the radian mode. Sometimes the homework is asked in the degrees and sometimes in radians, okay? And then for gamma, similarly, you do, oh, that's not correct. This is supposed to be 5. Okay, so because the z coordinate is 5, it's 5 divided by the square root of 38. That's the cosine of the angle gamma, and the inverse cosine will give you gamma as 35.8 degrees. And that sort of makes sense because this is taller than, 5 is bigger than 2 or 3. So this v should be closer to the z-axis. That makes the gamma smaller than the others. Okay, I trust you have gotten all of these correct. You will see problems like this on your homework. Incidentally, there's another interesting thing, almost mysterious because it works out so nicely. For any vector xyz, I mean like any vector xyz in three-dimensional space, if you do the cosine square of alpha, cosine square of beta, cosine square of gamma, add them together, and what do you get? Well, here, this is alpha square, oh, sorry, that's not, x square, right, over the normal v squared. Okay, all I'm doing is just squaring the expression for the cosine of alpha. And then the cosine of beta is y divided by the square root of the normal v. So then you square these. And then for z, you have this square. Okay, you add them up and what do you get? You get the denominator is of course the same. The top is x squared plus y squared plus z squared. What do we call that? Well, that's exactly the norm of the vector squared. So this is the same as the norm of v squared, and you get 1. Look at that. Wow. I mean, this is just as pretty as, the other one, which is sine squared plus cosine squared is equal to 1. This applies to all vectors, right? So, I mean, all vectors in three-dimensional space. So that's kind of cool. Okay, so the next subsection in section 2.3 is about projection. And so what is the projection? Well, many times you have to project a vector onto something else. And all that means is sometimes called the orthogonal projection. Let's say you have vector v here, illustrated by the first blue arrow. And then often you want to project it down to the second vector called u. Okay, so you notice here, this is perpendicular. And so this is called the orthogonal projection of v onto u. And the black vector that I drew here is called the projection of v onto u. Let me just make sure, v and u are so similar. You wonder why people have been using v and u. Why don't they use a and b? But this is the way you write this, right? So the projection of projection, we're trying to find the projection of v onto u, and in the standard notation is this. You write v big and u as the subscript after the letters P, R, O, J. Right? So this is the way you denote the projection of v onto u. What's the formula for this? Okay, how do you do this? You will study this extensively in linear algebra class because this is the basis of what is called the Gram-Schmidt procedure or Gram-Schmidt process. What we want to do is this, okay? What we want to do is to find the length of this. Okay, what kind of vector is this? Let's try to find this. Its length. Okay, how long do you want this projection to be? Well, from this triangle, it's pretty obvious. Okay, the length of this projection should be the norm of v, because that's the hypotenuse, times the cosine of theta, right? Because the hypotenuse times the cosine of the angle is going to give you the adjacent, which is the length of the projection of v that you are looking for, right? Okay, so this looks mysteriously close to something else, okay? In fact, we do this in algebra all the time, right? You kind of wish something existed in front because the norm of u times the norm of v times cosine of theta looks very familiar. It's something that we have been seeing for the last few minutes. But I can't just add, I can't multiply this by the norm of u and pretend like I didn't change this. Even if nobody's looking, you can't do that. But you can if you go ahead and divide it by the norm of u. See what I mean by that? I haven't changed the quantity, right? And of course, this is u dot v divided by the norm of u. Okay, that is a pretty simple. So that's the length of this projection I want. Okay, now, so the projection of v onto u is u dot v divided by the norm of u. Let's say this is 5, okay? So it means 5 units long in the direction of, what's the direction of this projection? Well, it's obvious, okay, because we're projecting onto u, so you want the direction of u. Okay, so can you, and the question comes out to be pretty easy, okay? The projection of v onto u is basically the vector in the direction of u with a length u dot v divided by the norm of u, right? So what is that? Well, here's my scalar. This is how long the vector is. And how do you write the direction of u? Well, you want to multiply this by the unit vector in the direction of u, right? I mean, the u could be a very long vector. I don't want to multiply this scalar by u because u could be long. If I want the length 5 vector in the direction of u, what I do is you multiply 5 by the normalized vector of u. So you have to divide u by its norm or the length because that's a unit vector in the direction of u. Let me emphasize this because it's easy for me to just give you the formula for this projection, but if you don't understand where the formula is coming from, it's no good, okay? Remember, I emphasized the deeper understanding of this. And by the way, sometimes I forget the formula for the projection, like if we have a long summer filled with the news about the epidemic or something, okay? But you know what I do? I just kind of create this whole structure. And then I remember, oh yeah, that's what the formula says, because it's the projection whose length is this, and this is the unit vector in the direction of u, right? And if you multiply the unit vector in the direction times the length, then you get the length, you get the vector that you want that has the direction and the length you want. So this is the projection of v onto u. Of course, it's not in a nice form yet, okay? So let's go ahead and try to make this simpler. Denominator, well, that's the norm of u squared, okay? And by the way, everything I've written so far is a scalar, right? You have a scalar number divided by a number, right? What's missing here? The only thing missing is this vector part, u, okay? So this is the projection of v onto u and its formula. There's something you can do even better than this, okay? So this is the formula I want you to remember. The projection of v onto u is the u dot v, the dot product, divided by, and remember how else you can write this? Yeah, that's u dot u. And then u comes in here. Look, everything is u except one V that you see on the top. Okay, so what is the projection of V onto U? Okay, it is U dot V divided by U dot U times U. Everything's about U. Well, it sounds like a cheap love song. Everything's U except V is right on top. Okay, so V appears only once as a part of the dot product. Everything else is U. Okay, all right. So that's your equation for the projection. Very important. Okay. Now, sometimes you also need to know this this vector, which I didn't tell you about. Okay, so this vector that's missing part, that's called the W. All right, what is this W? W is called the orthogonal complement. Do I want the word complement? Yeah, okay. Let me just expand on this. The orthogonal complement means different things in different contexts here. But in this context, W is simply the difference between V and the projection of V onto U. Okay. And so this is simply, in fact, a better way to say this is this. W is the orthogonal component when when one decomposes V in the U direction and the direction perpendicular to U. Okay, so let's say V is like a acceleration, or V is gravity, and U is some specified direction. And sometimes you have to decompose that force V into a given direction and the direction perpendicular to the given direction. Okay, like horizontal and vertical. So this W, okay, W is the component of V perpendicular to the direction of U. That's a better way to say that. And this is called the orthogonal component or orthogonal complement of V with respect to the vector U. Okay, I hope you get that, all right? But anyway, the formula, there's really no formula for this, except this is, I mean, that's exactly what I said. Maybe I will not write that, okay? So, because this is the formula, right? If you're asked to find the component of V perpendicular to U, or the orthogonal complement of V with respect to U, then you use that formula. Basically, find the projection of V onto U, and then subtract that from V, okay? I'm going to go ahead and use a different color to box this important thing here, what I just said. The projection of V onto U is, in its finest formula, it's the dot product divided by U dot U times U, okay? Now, of course, it's different if you do the projection of U onto V, okay? Then all the U's and V's will be switched. This equation will be almost all V's except one U that you will find on the top. One more thing here, this part, okay? Remember, this is all scalar. This is just a number. So this is a scalar product of U, which makes sense because you're looking for a vector in the direction of U. All right, we're almost done, except I need to give some example, and then maybe I have to just touch a little bit on the why the projection and the dot product is important in terms of things like work and physics applications, which are relatively important applications of calculus 3, right? But before we do that, let's go ahead and I'm going to give you an example. And I want you to figure this out, all right? So your V is 7, 4. Your U is 2, 3. Okay. Now you may choose to, sketch these vectors. And what I want you to do is to find the projection of V onto U. And its magnitude, how long is this projection? And find the orthogonal complement, okay? So go ahead and draw a picture. And then when you think you're done, you can come back and watch the last part of this video lesson. Okay.